Okay, so we're going to go over the practice problems from class today, covering the reaction types as well as acid-base reactions. So this first one is an acid-base reaction. It's asking us to write the reaction that takes place between ammonia, which is NH3, and acetic acid, which is HCH3COO, and both of those are going to be in solution. And when they react, the ammonia is going to behave like a base, the acetic acid is going to behave like an acid, so the ammonia is going to receive a proton. It's going to become NH4+, or the ammonium ion, so that's still going to be in solution. And the acetic acid is going to lose that proton and become the acetate ion, CH3COO-, and that's still going to be aqueous. So this behaved as a base, this behaved as an acid. The thing that is produced when the base receives the proton is the conjugate acid, and the thing that is formed when the acid loses a proton is the conjugate base. So our conjugate base is the acetate ion, our conjugate acid is the ammonium ion, and then obviously we have our acid and our base on the reactant side. Okay, let's take a look at writing conjugate acids and bases for these amphoteric substances. And we remember that amphoteric is a substance that can act like an acid or a base. So, starting with our substance, the conjugate base is what's going to be formed when our original substance acts like an acid, donating a proton. So if we take a proton away from water, what we're left with is the hydroxide ion. If we take a proton away from the hydrogen sulfate ion, what we're left with is the sulfate ion. And if we take a proton away from hydrogen carbonate ion or the bicarbonate ion, what we're left with is the carbonate ion. And when we take a proton away from the hydrogen phosphate ion, hydrogen phosphite ion, what we're left with is the phosphite ion. Notice that each time the charge is going down by 1 and the number of hydrogens is going down by 1. The conjugate acid is what's formed when this original substance behaves like a base and receives a proton. And so we're going to add a proton to each, so that's going to become the hydronium ion. When we add a proton to the hydrogen sulfate ion, we get sulfuric acid. When we add a hydrogen ion to the hydrogen carbonate or bicarbonate ion, we get carbonic acid. And when we add a hydrogen ion to the hydrogen phosphate ion, we get the dihydrogen phosphate ion, which still has a negative charge because this starts out at a -3. We only have a +2 here. Okay, so determining types of reactions. When we look at zinc and hydrochloric acid, the zinc is replacing the hydrogen. That makes this a single replacement reaction. Because the zinc is going from no oxidation state to a +2 oxidation state, this is also an oxidation reduction reaction. Magnesium plus oxygen forming magnesium oxide. This is a synthesis reaction. We have 2 elements combining to make a compound. It is also an oxidation reduction reaction. We can also classify this as a combustion reaction because this is a reaction that gives off heat and light, sometimes even flames. All right, we have our hydrogen peroxide decomposing into water and oxygen gas. This is a decomposition reaction. We're starting with one reactant and forming multiple products. This is also a redox reaction. Okay, this one we have mercury 1 nitrate and hydrochloric acid forming nitric acid and mercury 1 chloride. And so this is a double replacement reaction. It is also an acid-base reaction because this hydrogen is being donated to something else. It is also, when we notice this solid, a precipitation reaction. So we have 3 different categories there. When we look at the perchloric acid and ammonia reacting to form ammonium and perchlorate, we have an acid-base reaction because we have a donation of hydrogen to ammonia to form the ammonium ion. And last one, we have a hydrocarbon reacting with oxygen to give us water and carbon dioxide. So this is a combustion of a hydrocarbon reaction, and it is also a redox reaction. These are not balanced. Okay, last one. This tells us that equal volumes of these 2 equimolar solutions of ammonium iodide and lead 2 acetate are combined and a precipitate forms. So our balanced chemical equation, well, we have NH4I. We know because it contains ammonium that it's soluble, so we're going to write that this is aqueous. Also, it tells us it's a solution. And lead 2 acetate, PbCH3COO2. This one is not part of the SNAP rule, but you might remember from honors chemistry that acetate salts are also always soluble, so that's why this lead is soluble. But again, it told you in the stem of the question that these were solutions, so you know that that lead 2 acetate has to be dissolved. And a precipitate forms. So we're going to have a double displacement reaction, so the iodine is going to replace the acetate is going to replace the iodide. We're going to have NH4CH3COO, and that, because it contains ammonium, is going to be soluble. And we're going to have lead 2 iodide, which, because it does not contain any of those, and because we remember that lead is insoluble unless it's with acetate or nitrate, is going to be solid. So there's our precipitate. We need to put a 2 here to balance the 2 acetates here, which means we need to put a 2 here as well. We could write a net ionic equation for this. It wasn't asked for, but that would be 2 iodide ions plus the lead 2 ion form lead 2 iodide. Not aqueous. Solid. That's why we have a reaction. Okay. Draw a molecular model to represent the products in this reaction. Include a key. So we have our beaker, and at the bottom of our beaker we have some lead 2 iodide. And in our solution we're going to have some ammonium ions. And we're going to have some acetate ions. And that's what our product beaker is going to look like, making sure that we have the lead 2 iodide at the bottom. Okay, so that's 4.7.